So let's continue to develop our ideas with work and energy. First of all, we have a simple equation for work. Work equals force times distance, which only is good if we have a force and a displacement vector that are aligned with each other, either both pointing in the same direction or they're pointed in opposite directions, in which case we'd have a negative work being done. Well, what happens if there's an angle between the two? It doesn't matter where the angle is. It could be some crazy angle between the two. One could be horizontal, one could be vertical, whatever. We need a way to handle that general idea of having an angle between the two vectors. Secondly, if we were to create a graph of our force versus the displacement moved for an object, for example, the displacement graph shown to the right, what could we determine from that graph? What does the slope mean? What does the area mean? You'll recall that we had a graph of force versus displacement with our spring lab, and so this will help us gain some insights into the meaning of slope and area from our spring lab. So let's start by looking back at a former quiz. We had a grandmother pushing her lawnmower along a sidewalk, and she's pushing along the handle with 100 newtons of force. So we have an angled pushing force, and the displacement is to the right, so we have a horizontal displacement force. So this would be a good example of two vectors that are at an angle, a force and a displacement vector at angles that we'd like to calculate the work for. Now, the method we used to solve this problem, and we were asked to find how fast the mower is moving after pushing it for 5 meters. What you did is you drew a free body diagram first, and so here's our free body diagram. We have a 15 kilogram mower. We have the force being directed down the handle. Draw some dimensions. Here's our gravity vector. We've got a normal vector, and the normal vector will include a 50 newton contribution when we break down our pushing vector along the handle. We've got 50 newtons downward and 86.6 newtons to the right. This is a 30, 60, 90 triangle. In this case, we had a 30-degree angle that the handle was making with respect to the ground, and as you recall, our half of 100 gives us the short side, and square root of 3 times the short side gives us the longer leg of that triangle. And that's why we have a 200 newton normal force. From that, we had a mu k of 10% for this problem, as you recall. And so we have a 20 newton frictional force counteracting our motion that is to the right. The next thing you needed to do to find how fast the mower was moving was to find the acceleration. And the acceleration is to the right for this process. The person is pushing to the right, it will accelerate to the right. And to find that, well, first of all, you needed to assume constant acceleration, and we applied Newton's second law, and we could find the acceleration, which we found to be 4.44 meters per second squared, and then we used equations 5 and 6, or we could have used equation 8, which is a little bit quicker, using the acceleration, our displacement, and our initial and final velocities. We can find our final velocity. And we found that the final velocity is 6.66 meters per second. That we call the kinematic way of doing it. The study of motion using equations, modeling with equations, is called kinematics. Now, in Chapter 5, we can use energy. We still need to start with finding a free body diagram. Any type of problem that has forces in it, you should always draw a free body diagram. You'll find that it comes in handy. So here's our free body diagram, same free body diagram, and then we would apply the work kinetic energy principle with the simple equation for work equals force times distance. Now the problem with this equation, and in this particular problem and situation, we have our displacement is to the right, our frictional force is aligned with it, it's going the opposite direction, so we'll get a negative work contribution from friction. But the problem we have here is our pushing force is not aligned with the displacement vector. It's at an angle. So that's a problem. We can't use our simple equation unless we were to knock out this pushing force that's at an angle and just replace it with its two components. We have the downward piece and the piece to the right. So we just break it down into x and y components. Now we have vectors that are aligned with each other. You'll notice that both of our x vectors, fpx and ff, are aligned with our displacement vector. The frictional force is opposing it, that'll be a negative work done, and the pushing force in the x direction is aligned with in the positive direction. We'll get a positive work contribution from that. And all three of these red ones, they're perpendicular to our displacement vector, and we've got no motion in the y direction, so the work contribution by the three red vectors is going to be 0. So now that we've broken our vector down, we simply can use these newly aligned vectors to take care of our problem. We can use simple work again. So let's use our work kinetic energy formula, and let's see how we would solve the same problem that we did using chapter 3 and 4 concepts with chapter 4 and 5 concepts. So the net work equals the change in kinetic energy. That's the work kinetic energy theorem. And I'll just break down. Remember, net work just means to add up all the components of work from every force. Well, we've got 1, 2, 3, 4, 5 forces, and there are 1, 2, 3, 4, 5 sources of work. And delta KE is just our final kinetic energy minus our initial kinetic energy. We'll zero out our initial velocity started at 0. We can also zero out all of our y components that are perpendicular with our displacement. They don't contribute any work. There is no work being done in the y direction. It's all being done by the x forces in the x direction. And we know that the frictional force will be negative, so I can throw a negative in there. And if I crank out some numbers here, and you can see that negative there, you could also consider the fact that our frictional force is negative, would provide that negative as well. And so now we have two components remaining. We have done by our pushing force right here. And to the right, we have our work done by friction here. And I've plugged in some numbers here as well. So I'm doing this by plugging in numbers rather than doing a general solution for this problem. And we'll see later why a general solution can be useful as well. I sort of like when I'm doing work formulas and energy calculations to plug in numbers because, as you can see in this next step, I actually get to see how many joules are contributed, how much energy in joules is contributed by each force. If I were to start canceling out variables and moving things around, I wouldn't have as much visibility into what the work was done by each component. So this is sort of nice to have this. And we can see that there is 433 joules done by work done by Granny pushing, and we have 100 joules working against Granny. One question you might ask yourself is, where does this lost friction go to? We know Granny's work is done accelerating the vehicle, but she's losing 100 joules to friction, and where does that energy disappear to? I think you probably have a good idea what the answer might be for that. When you actually work this out, subtract these two numbers, divide by 7.5, take the square root of v, and you'll get 6.66 meters per second, and they match. So this method works. And you'll see, after you do this a few times, that arguably the method using energy tends to be a little bit quicker than the method using motion equations. And a big time-saving hint when we're working with the energy, once we write out everything in this formula here, it's best to go through and just knock out everything that's going to be zeros, or to flip in your negatives at that point. And we had several things that knocked out up front and made it a very easy calculation to do in the next line. So let's just compare what happened in these two steps. When we were working with the chapter 3-4 method using kinematics, well, pros and cons. Well, the biggest con is that we have to calculate AX, and that's sometimes a lengthy calculation. We have to use Newton's laws after we come up with a free body diagram, and it just takes some time and effort to do that. On the other hand, one thing that this method does do that work does not is that it also gives us a time, if we were to want it, of the objects as they were going through time and space. So it gives us time, and because everything in these motion equations relates to vectors, it also gives us directions. And on the flip side, the work energy methodology, you don't know anything about time, you don't know anything about direction. However, like I said, I think you'll find over time that as long as you don't need time or direction, the energy method tends to be pretty quick. All right, and the direction in some cases you'll know just because it's going up, down, left, or right. If it's at some angled vector, if you're going through with like a 2D motion problem and you're flying through the air, you'll lose that directional idea. But in any case, it is a quick calculation. And finally, the bottom one is probably the most important reason you'd want to use energy in some cases is because your acceleration does not need to be constant. You don't even use acceleration to do work equations. And that's a huge advantage if you have a situation where acceleration is not constant. And of course, in the real world, there's lots of situations where that happens. So keep an eye out for that. And when you find out there's a situation where acceleration is not constant, go ahead and look at an energy solution for it. All right, so let's just see. Let's just summarize what's going to happen. What happened when we did this decomposition. So we applied the work kinetic energy principle, and essentially we killed our unaligned vector and replaced it with its decomposed vectors, and then we just were able to plug these into our equations and come up with a result. All right, but in reality, that was a lot of work. A little bit of work. And really, all we really wanted to get out of that is this component right here. The perpendicular component was completely useless to us. We know it was going to zero out and there's no work done to it. So really, it would be nice if we could have a process that ignored that y component and just focused on picking out this x component for us. Is there some magical vector function possibly that pulls out that force in the x direction and ignored the y direction? And it turns out there is. It's called a vector dot product. So let's take a look at the vector dot product. Well, first of all, we need some type of formula that takes care of a sign for us. It should give us a positive or negative sign, and only picks out the portion of a force, or the distance, as you'll see later, that is parallel to the other vector. The perpendicular piece we want to ignore. And so the mathematical function we'll use to do this is called the dot product. And I use a big fat dot just to make it stand out, but literally you put a dot in between the two and you should show vector notation above both. And these are the two vectors, force and distance. And it turns out the resulting quantity coming out of this calculation is a scalar quantity. Work is a scalar quantity. And when we do this work, what we're going to do is we're going to take the magnitude of f, which is just our f right here. We're going to multiply it by cosine of the theta, and that gives us our f in the x direction in our previous case. And then we multiply it by the magnitude of d. In short, we typically say this is fd cosine of theta. And we'll see that, we'll revisit that a little bit later and see if this is a commutative function or not. And keep in mind that all these parts of this process, our work and all of our components when we're doing the calculations using fd cosine theta, these are all scalar quantities, not vector quantities. So it looks like our trigonometric cosine function does what we want it to do. That's our magical function that we use as part of what we define as the dot product to isolate the parallel portions of these two vectors so that we can multiply them together like we've done before in the simple work equation. So let's go back to our Mohr example. Let's try this out. So what I've done is I set up a little table here so we can just list out our forces. And you've seen me before use tables to line things up. When I'm actually working these out in equation form, I would typically write a long equation just listing everything out. But this is a nice way to summarize things. And I'm going to list out the forces that we're going to work in our formula fd cosine theta, and then I'll list all the distances, and then we'll list all of our angles, and then we'll actually do the work and see how it works out. So our forces, remember, we're using the magnitudes of all the forces. There are no signs involved here. Our sign will come out of using cosine of the angle. All right, so we're going to use standard angles on these quantities, and that will take care of signs for us, both the positive and the negative sign. The displacement vector, which I call d, when in reality we know it's delta x or delta y, or better yet delta r in the polar format. What that is going to do is we want to use the magnitude of that. And we're going to use the magnitude for every single one of these, even the ones that we know are going to end up with a 0. What will handle zeroing things out for us? Once again, our trig function will do that. Our cosine will do that for us. So the question is, on the first case up here, we want to take the dot product of this force, the purple force, with this green displacement vector here. The problem is, what's the angle between this guy way over here and this guy over here? Well, the problem is these guys are sort of physically separated from each other and pointing in crazy directions. So I'm going to make a little shift here. And I'm going to move these all to a common starting point, which is one of the reasons I like to draw all of my vectors pulling on a box rather than pushing on a box, as you see here. And we can do this because as long as we translate the vector, translated vectors, we can move it as long as we don't change the length or the direction, and it is the same exact vector. And that's one of the rules of vector mathematics, is translated vectors have the same meaning as untranslated. So here I'm going to translate this vector, and you'll notice when I do this, I get this nice formation with not only with my displacement, my pushing force, but you can see my displacement also works nicely with this orientation. With this one I can see an angle between them. With the frictional force I can see this big angle between them, and with the gravitational force I can see this big angle, and with my pushing force I see that angle. So what is the angle between the pushing force and the displacement? Well, that angle is 30 degrees. So we have a 30-degree angle right here, and that was the angle that our mower was making with respect to the ground, the handle, and we're using a, if you look in geometry, it's a vertical angle that we use to show that that was the 30-degree angle from before. Let's just go through our other angles here. What's the angle between our normal force and the displacement? Well, I'm going to use the displacement as a starting point, and I'll move over this way. So I've got from here over to here is 90 degrees. All right. And for my displacement over to my frictional vector, I go from here over to here, which is 180 degrees. And my gravitational force, I start from the displacement all the way around counterclockwise to my 150 degrees, and to my 150 Newton vector, and that is 270 degrees. Now, one thing you may be asking is, well, aren't I doing this in the wrong direction? If I'm going from the force to the distance, like I did in the first case, I went from the purple vector clockwise or counterclockwise to the green vector. So in these other cases, if I was doing the normal force dotted with the displacement, shouldn't I start at the force and work around counterclockwise like this and come up with a 270-degree angle versus a 90-degree angle? Well, that's a good point, and we're going to hit that later, but it turns out it doesn't matter which way you do it, is a quick answer to that. So let's just take a look at our answers here. If we just plug in our numbers, and remember we're plugging in all the magnitudes here to see this, and I color-coded things a bit so you can see this 100 Newton came from this purple vector. We've got our 5-meter displacement times cosine of 30 degrees, which is square root of 3 over 2, and we get 433 joules. Positive, all right, which is exactly what we got before from the first method where we broke down the purple vector into its two components and then took the components and multiplied them. You can see that our magical dot product did that in one step without having to think about the decomposition of the x component. It took care of the parallel piece for us. Similarly, if we go to the normal force, you'll see that this dot product also takes care of zeroing out things that are parallel. I'm sorry, that are perpendicular. So just what we wanted here, we only wanted to, using this magical equation here, end up with parallel portions that affected our work and reject all the perpendicular portions, and you can see that happened here. In our frictional force, those are going opposite directions. The other thing we want to do is take care of negative signs for us, and cosine of 180 is, I'm sorry, that should read -1. So put a -1 there for me. And on this last step, we've got our gravitational force, and that's going to be perpendicular, so that should be 0 out, and it is. I'm sorry, and you can see here I swapped my 0 and -1 here. And what we end up with, if you look at our results, we have 433, positive 403 joules that we had before. We had no contributions from the normal force or the gravitational force, and we had a -100 joule force from our frictional force, which we had in our problem before as well. So this dot product worked out just as we expected. It's a nice clean way to do the math. So let's just see how this works out when we look at the problem as a whole. So I just took this free body diagram, and we're going to apply the new dot product methodology to it. So we're going to have to lay out these two vectors, and then we're going to take the magnitudes of each and multiply them by the cosine of the angle between. So here's our network formula. Here's all of the forces, 1, 2, 3, 4, that we're considering. All right, and I'm not going to break this one down into components. I'll let the dot product do it for us. And let's just zero out some things right off the bat. We know that our initial velocity is 0. And you know that these other two components that are perpendicular to our displacement, which I just flew in, these will end up being 0 as well. But let's just let the dot product show us that real quick. I'm going to translate my pulling force to make it easier for me to see the angle between these two vectors. And formally, we take each one of these values and we work it out. And you can see I use a different angle here just to show you how this works. I've got my pushing force and my displacement, and now I'm going to use, we'll see if this works, my angle from the displacement all the way over to the pushing force, which is 330 degrees. Well, ask yourself, is cosine 330 degrees the same as cosine of 30 degrees? For that matter, if I want negative 30 degrees down clockwise, that's the same as well. So it really doesn't matter which angle you use. If it's a standard angle, as long as it's the angle between the two, whether you're taking the external angle or the internal angle, that's fine. And you'll notice that we have cosine of 90 between these two, cosine of 270 between these two. So these two red ones are going to zero out, and the cosine of 180 is going to give me a -1. And sure enough, that's what happens. And we could have, of course, done that right up front, which I typically do, and which is what you should do when we're solving these problems in a quicker fashion. I wouldn't even bother writing out this work down here. I would just be zeroing them out in the line up above. And once again, the values that we saw before pop right out using this new method of using what we call a dot product. All right, we get 6.66 meters per second. So how to deal with strange angles, and does the dot product order matter? I've already referred to that a little bit. So here's our two angled vectors, and as you can see, if we have things that are not nicely put together for us, we can shift things around a little bit, do a translation, and identify our angle, and it's 30 degrees in this case. And here's our formula, and we calculate, we get 433 joules. That's our dot product formula. Now, let's just see, does dot product order matter? So let's reverse the dot product here. Let's do d dot f instead of f dot d. And so what we're going to do is we're going to reverse the angle here, and we're going to go from d down to f instead of from f to d. And now we have an angle of -30 degrees, or you could also consider, if you look at the going in the standard direction, we could have a positive 330 degrees. And if we were to do the two calculations for either of those angles, you'll see that it doesn't really matter which way we do this. So it looks like that the dot product order doesn't matter. In other words, the dot product is commutative. It has a commutative property, just like multiplication does with scalar mathematics. So, and that comes out because of our force and our distance multiplication over here. We multiply distance times force. We commute the two, and we're just using commutative property of multiplication to do that. And in the same sense, we find that cosine of 30 and cosine of -30 and cosine of positive 330, this should be a 330 degree angle here, from trigonometry all turn out to be the same value. And so trigonometry works perfectly for us to work out the dot product. Now, there's another way to explain why this commutation works. And let me give a case here. It looks up here as if we have d cosine of 30. So it looks like we've taken our d vector, our displacement vector, and multiplied by the cosine 30 as if we're decomposing it in the x direction. In other words, if we were to draw a line parallel to the force vector and decompose the distance vector with respect to that line, then we'd end up with, and I'm sorry, this blue one should read dx. The dx component and the purple component, once we do this d cosine of theta, gives us two aligned vectors that we can now use. In the same sense, if we take the second case, we could argue in this case, it looks like we have f cosine of 30, which looks like we've taken our force vector and pulled out the x component of it. So it looks like we're finding the x component of the force vector. So let's just see. So we're going to find the x component of the force vector with respect to the d component. So there's our line that we're going to break this force component down against. And as you see when we break this down, we have our x component, and that should read an x right there. That's perpendicular and our perpendicular y component. And when we use a simple work formula, work equals force times distance, we need two aligned vectors, and there they are. Just like we got two aligned vectors over here, we ended up with two aligned vectors over there. And if you'll notice, here the distance vector retains its full length, or magnitude of 5, and our force vector is multiplied by the cosine of this case, and just the opposite occurs here. And if you look at the math and you work it out, you'll find out that it doesn't matter, you get the same result in the end. So finally, let's look at some big ideas here. So keep in mind that when you're using the dot product of two vectors, that the result is going to be a scalar result. All right, so these are vectors. So this is called a vector dot product, and the output of this is work, which is a scalar quantity. And remember that when we actually turn this dot product into some math we can crank out, we use the magnitudes of these values to actually work these things out. So everything I have circled in blue here are magnitudes. And remember on this as well, the value of this, even though the work is a vector quantity, I'm sorry, it's a scalar quantity, it could be positive or negative. And that gives it an idea of if the work is going into the system or out of the system. I do have an extra practice problem that you can work on, and this is you can do this for extra credit for homework practice, and you can go through two scenarios of dragging a box at a constant speed for 2 meters at 4 meters per second speed, and then increasing that with an acceleration of 3 1/3 meters per second for 2 meters with an initial velocity of 0, and compare the work in each case. And if you go through these two problems using this process, I'll give you some extra credit. I asked you to take a look at this situation. We've already discussed it a bit in class, and I asked you to use your old-fashioned method of chapter 3 and 4 methodologies of figuring out if you had a block dropping 3 meters straight to the ground, and you compared it to a block, same block, which would slide down this ramp. And in the first case, we had a ramp that was frictionless. In the second case, for part C, a ramp that had a UK of 20%. I asked you to find, number one, what's the velocity at the ground, and number two, what is the time it takes to get to the ground. And I asked you to rank order these as well. And I think when we voted in class, the time it takes to get to the ground, people did a really good job on. I think you figured that out perfectly. The velocities, though, it turns out you ended up with an interesting result. And let me just summarize what that result is at the end. What we found was that it turns out that the one that slid down the ramp with no friction and the falling box ended up at the ground at the exact same speed. And by the way, if it's the same speed, it means they have the exact same energy if you consider the kinetic energy. That was a surprising result. Most people did not get that when we voted. Not surprisingly, the one with the friction actually had a lower speed and a lower kinetic energy. And for that method, you use Newton's second law and use motion equations to do that. And we could also use those same equations to figure out times. And as you correctly predicted, the one dropping hit the ground first, the one without the friction hit second, and the one with the friction hit last. And we probably used equation 6 to figure that out. Now let's take a look at this problem again, but this time let's use energy methods to see what happens. So first, let's consider the case where we have the block dropping straight to the ground. All right. So we're going to use chapters 4 and 5, energy and work methods, to do this. And just as we did before, we will need a free body diagram to work out this process. There's forces involved to calculate work, so we need a free body diagram. And so this is a really simple situation. Here's our coordinates we're going to use. And we only have one force of gravity acting downward. That's it, free falling. All right. So now let's use work kinetic energy principles, and we have a new dot product methodology we can use. And so we hit net work equals change of kinetic energy. And if we break this down a little bit, the only work that we have being done is by gravity. There's only one force on this, so we only have one component of the network. And our kinetic energies are final minus the initial. Of course, our initial value for velocity is 0, so we're going to knock that out. And we can substitute our new and improved work formula, which is FD cosine theta. We're using the dot product. And so we're going to take the dot product between these two vectors. All right. I guess the big question here is, what's the angle between these two vectors? So you've got to get a little bit of practice figuring out the angle between them. And the angle between these two vectors is 0. If you look, the angle is right in between these two. They are pointing the same exact direction. So the angle between this and this, there is none. They are in the same direction. So don't get fooled by this. So we're going to go ahead and plug that angle in. And of course, cosine of 0 degrees is 1. And if we plug in some numbers now, so our gravitational force is 200. And you'll notice I'm using magnitudes here, and I'm going to let this cosine give me my signs here for my forces acting. So I have 200 newtons for my magnitude of my force. My magnitude of my displacement is 3 meters, and this positive 1 shows me that we're going to have positive work done. They are aligned with each other. That's what that says. I can go ahead and finish solving. I like to see the amount of energy before I do that. So I've got 600 joules of work that's being done by gravity. And that's positive work being done. The question is, what does gravity do? What's the outcome of that work? Well, in this case, the outcome of gravity's work on this is it makes the thing go faster. Remember what we said. If your network is positive, that means you're accelerating, so your speed should increase. And that's exactly what gravity did. It increased the velocity of this object. And if you solve for v1, you get 7.75 meters per second. Same result we had before. Very easy problem to calculate. Of course, I think motion equations are just as easy on this because we didn't have any complex free body diagrams to work out, and it's quite easy to use probably equation 8 without much thought as well. So that's a pretty easy situation here as well. Okay, let's take a look at the blocks sliding down the ramp. This one takes a little bit more work, whether you're using chapter 3 and 4 or 4 and 5. And what we're going to need to do is draw a free body diagram. Do we need to rotate axes? That's one question we could ask. Here's our force vector acting downward. I drew a little bit exaggerated this time just to take this whole distance down. And we've got a 200 Newton force acting downward. We do have a normal force acting up from the ramp perpendicular to the box. And now we will apply the work kinetic energy principle. So the question is, where's the displacement here, and what angle will we use to calculate our work components? So we need to calculate the net work done, which means on all of the forces acting on it, so that we have two forces to work out. So we've got a work done by gravity, and we've got the work done by the normal force. And this should have an Fn for normal force right here. And our delta KE, of course, is the final kinetic energy minus the initial kinetic energy. Of course, we're starting from 0, so this will zero out. And let's just see what else zeroes out. Well, I say that we're perpendicular, but I actually haven't drawn in my displacement vector yet. I hope I draw it in soon here. There's my displacement vector. So my displacement vector is right here, and you can see these are perpendicular. That's why I zeroed out my work done by the normal force. It is perpendicular to the motion. So for my work done by gravity, I'm going to use my dot product methodology. So I'm going to take the dot product of these two vectors, which is the force vector, the magnitude of the force vector, times the magnitude of my displacement, times the cosine of the angle between the two. So the question is, where's my angle between these two vectors? And I think from our practice before, it should be pretty apparent where that is. We can use that angle right there. Or we could use that angle right there for that matter. We saw before, it doesn't really matter which one we use, a standard angle or a non-standard angle. It's very flexible formula. So let's go ahead and plug that in. I'll use a 30-degree angle. And this happened to be a 3, 4, 5 triangle we were on, so I didn't actually have an angle per se. You could use trig to figure out the angle was. But as long as I have the sides, I can, a cosine is just a ratio of two sides in any case, so I'm just going to throw the two sides in for the cosine of my angle. So I'm going to substitute 3/5 in for this. And you'll notice 3/5, those are unitless numbers because the meters cancel out. And we can go ahead and plug in numbers here, and we can come up with an answer. Wow, look at that. That's interesting. We went down the ramp, and we found out that the force pulling it down the ramp, which is not actually acting perpendicular to the box anymore, is still 600 joules. So this is an identical result to the last problem that we did. So it didn't matter if we went down the ramp or we dropped straight down. Gravity did the same work on the box. And as a result, the speed at the bottom is 7.75 meters per second. Of course, how long does this take to get down the ramp is the other question you could ask. With energy, we can't figure that out. Energy doesn't tell us anything about time. So you want to use a little bit of logic on this. And I'm going to let you, there's a worksheet coming up where you'll have to apply a little bit of logic to see if you can figure out what's happening with times and things. And I'll hold off on that and let's see what you come up with. So quite an easy problem. As it turns out, we didn't need to rotate any axes, which you probably did when you worked out the problem using kinematics, Chapter 3 methodologies in Chapter 4. And so using this dot product is quite easy when we're finding work. Now, let's see what happens when we add some friction to the situation. So, once again, will we need to rotate axes? Well, let's see. Well, first of all, we need forces to figure out things. So the first thing we'll do is work out a free body diagram. Same thing as before. We have our force due to gravity. We have our normal force. And this time we have a frictional force acting against us. Now, the problem is, in the last case, I didn't have to go beyond this. I could just use these values. But now I actually need to know the normal force value in order to calculate the frictional force value. So I will need to break down my gravitational force into vectors so I can actually calculate the normal force. So I have to do a little bit more work this time, but it's easy. So that's my breakdown, perpendicular and parallel to the ramp for my gravity vector. And I just threw in an angle beta down here and beta up here to show you that the angle here and the angle here, these are similar triangles. So this one is 3, 4, 5, and on the same triangle over here, we've got a 3x to 4x to 5x relationship. And so these are both similar triangles, so the ratios of the sides will be identical. And so we can use sine, cosine, and tangent in a simple way, just like we did before, without actually having to calculate angles if you don't want to. If you do want to calculate angles and use an angle with sine, cosine, and tangent, feel free. So we can use this to calculate the normal force in the y direction, and this should say, if we take the gravitational force in the y direction, that will equal our normal force in the y direction. In the same sense, we can calculate our gravitational pull down the ramp, which is 120 newtons. And our normal force then is equal to our force due to gravity, which is 160 newtons. And if we multiply that by 20%, 2 times 16 is 32. So we get a 32 Newton force acting up the ramp. And so now that we have all of our forces, let's go ahead and we will apply the work kinetic energy principle. And we'll use some dot products again, practice using a dot product to calculating works. So there's our formula for the work kinetic energy principle. And we have, I'm going to use our three primary forces here. This purple one from gravity, the normal force, and the frictional force. I'll pretend I didn't even have these two broken down components for gravity, just so we can practice using the dot product. And here's our result. Just jump right to the solution here. For our force done by gravity, just like before, we have Fg. There's our force vector dotted with a dot with the displacement vector times the cosine of the angle, Fd cosine of theta, which we have right here for the dot product methodology. Our frictional force, same formula. Our normal force, I'd zeroed out because these are going to be perpendicular. I don't want to waste any time. We'll probably want to show up here, probably in one of my next couple of clicks. There's my displacement vector, so you can see this right angle. And we also know that our frictional force, because we have a 180-degree angle here, they're working against each other, that this should end up being negative. All right, and you can see right down here it is negative because we're going to put 180 degrees in for the theta. And so our angle between our force due to gravity and displacement is just as it was before. It was, turns out that's a 36.9 degree angle if you wanted to calculate that, but we know the cosine of that is 3/5. We can plug that in. For the frictional force, once again, I mentioned that's 180 degrees. When we plug that in, that's just going to be a -1. And that's where this -1 down below comes from, and this 3/5 here comes from. And you'll notice what happens is, if we plug in these numbers without trying to solve for v too quickly, which is opposite of what I typically do. I like to typically jump right to a general solution, but for work and energy, I like to slow down a bit and see the numbers, because I love to look at the energies involved with each one of these components of work. So here's the work done by gravity, and once again, as in the previous two cases, the work done by gravity is still 600 joules. So gravity is still trying to, in a positive sense, positive means causing it to accelerate with 600 joules. However, if you look, we've got a negative component due to friction, which is slowing it down. All right, so we've got overwhelmingly a number here speeding it up, but then to some extent we've got friction slowing it down. All right, one thing you might want to ask yourself, all right, so it is slower at the end, not the same number we had before. One thing you want to ask yourself is, well, what is this work done by friction, which is negative? If it's not helping speed it up and slowing down, where does that energy go to? So we know that the energy from the box sliding down the ramp turns into kinetic energy, speed, motion energy. But the frictional energy, where does that negative energy go to? It gets sucked away somewhere. Where does it go? So here's the next homework, and I may not have this printed out for you, but I'll post these slides online so you could print it out or write down the answers and copy down the questions neatly if you would, please. But let me just give you a little summary of the results here. And once again, you can print these out online. And I'll put this out in a full page format for you. Let's just look at our three results that happened here. What we have in the first case, we had a box that dropped straight to the ground. In the second case, a box on a ramp with no friction that slid down the ramp. And in the third case, same ramp, same box, well, we add some friction to the ramp, put some peanut butter on there, and it slowed it down a little bit. And here's a quick summary of the math in each case, and you'll notice that in these two cases, the velocity at the bottom was the same regardless of which of the situation. So the path did not affect the speed at the bottom of the ramp. And that's really an interesting result. And that's a key result that we're looking for that will help us out with the next idea in energy and conservation energy that we're going to go into next. On the other hand, in this case, we had very similar numbers. So there's our 600 joules of energy that we saw over here and here. But we have this negative energy due to friction that slows us down. So let's just look at some questions. And what I would like you to do, I would like you to answer these 4 questions for me. All right, and then we'll talk about the correct answers in class. So in case A and B, gravity did all the work, but through a different path in each case. In the first case, it went straight down. In the second case, it went down a much longer path at a slope. In part C, friction also did some work. All right, here's my question. This relates to friction. Is work done by friction, or this is a true or false question, so here I'm going to give you a statement. Work done by friction will always be negative. Is that true or is that false? And I want you to explain your answer for that. Is work done by friction always going to be negative? And think about how we defined friction in the past, and I think you'll have an easy answer to that one. Second question. A and B, we saw, ended up at the same speed and the same kinetic energy down, regardless of the path. Can you explain why that happens? Thirdly, suppose you were to take box A, and instead of let's let A and B, they're on the ground now, and you want to reset the problem. All right, so you're going to take A and lift it back up, and you're going to take box B and you're going to push it back up the hill, and both of them will go back to their starting positions. If you were to do that, which one of these processes would be harder for you to do? Would one take more effort than the other? All right, lifting up A or pushing B up the ramp? And secondly, which of these situations would require more work for you to do to reset those situations? So does one take more effort, and does one take more work? That's the question. And I have a slide next that you can use to work out that answer on. And then the next question I have is, why did box C end up being slower than the other? Where did that missing energy go to? And we have this missing energy, this 160 joules. Where did it go to? And why is it slower? So here's the slide. Here's a slide that you can use to answer the question about which one would be harder for you to do. And what I want you to do by harder, by the word harder, I mean which one is going to take more work, more muscles for you to lift. All right. In other words, look at the forces. So calculate the minimum force required in each situation to push this thing back up to where it started. All right. In terms of work, once you calculate the minimum force, you can use the work equations to calculate the work done in each case to reset these situations. And thirdly, this is worth some bonus points. If you could tell me where we've seen a situation similar to this in class, it doesn't look like this, but it has the same result. Take a look at questions number 1 and 2, and then see if we've seen something similar in class, and you may that'll earn you some bonus points. So first person to come up with an answer for that. And if you send me the answer on social media, if you're watching this online, before anybody else does, I'll give you the bonus points first. Now, here's the other slide I want you to take a look at. The question is, what would happen if we change the ramp shape? All right, so we're going to still keep the same mass of the object, and we're going to have the ramp frictionless in each case. And here's our baseline situations up here. We've got block A and B, and we dropped A, it went straight down to the ground. Block B slid down the ramp. In both cases, these ended up at the same velocity. All right. The question is, what would happen if we changed the ramp to look like this shape, all right, or this shape, or this wavy shape, or a really, really stretched out long ramp? The question is, would that change the situation at all? And what I want you to do is, and you'll have this slide you can print out, and it'll be a full-size slide. You can answer these 5 questions. I want you to try to rank order for me which box will be the fastest to the ground or the slowest as it reaches the ground. And I'm looking at the speed you have at when you reach the ground with the block. So I'm looking for the final velocity at the ground for each one of these cases. So I want you to rank order which one will have the fastest speed at the ground and which one will have the slowest speed at the ground, and work out the whole order the best you can. Remember, this is a little bit of guessing, a little bit of logic. See what happens. The second one deals with time. I want to know which one reaches the ground first and which one reaches the ground last, so you can rank all the other ones in between. So can you figure out the time each one takes, roughly speaking? And I'm not expecting you to do any calculations to answer any of these questions. I just want you to sort of think about how to answer these from a general idea, and you should be able to do this. And don't worry if you can't get a good answer. In class, we'll talk about how to strategize this. Here's a good question. You'll notice I have normal forces acting in any case where the object is touching another object. So anytime we're sitting on a ramp, we have a normal force. All right, so just to practice a little bit of practice with normal forces. Which of these objects has the largest or smallest initial normal force? All right, so from their starting point on this object, you'll notice I tried to keep the normal forces all the same length, even though I'll tell you right now the normal forces have been changing depending on how I set these on the ramp. So which one would have the longest normal force or the highest normal force? Which one would have the smallest? And finally, or this is the second to last question, speaking of the normal force, will a normal force ever contribute to the work done on an object? All right, so think about that. And finally, we've seen in certain cases when we're doing things that are Chapter 3 and Chapter 4 with objects that are accelerating, that mass doesn't matter. The question is, for these energy situations, can you show that mass doesn't matter? What would you need to do to show that mass doesn't matter? And do you think mass matters or not? We've seen it in our kinetic energy equations, so it's in our equations. So the question is, does it matter or not? And how would you show it? So that's your homework. Good luck, and we'll talk about more in class.